Hello everyone. These are notes 5D.2. 5D.2. In this lesson, we're going to be talking about attributes and transformations of cube root functions, function operations, inverse functions, and composition of functions. Now, pretty much for the most part, this whole lesson should be a review. It just involves the cube root versus any of the other parent functions. But we've done this for every parent function we've looked at. So let's get started on the lesson. Now, just like we did for the cubic function, let's review the cube root function. So it's y equals the cube root of x. Here's our parent function table. Now, if you remember, the cube root and the cubic function are inverses of each other. So therefore, the graphing table is just the flipped or the inverse of the cubic function. So when we graph it, it looks like that. So it kind of looks like a little sideways snake there on that graph. So if we look at the domain and range, obviously it's going to keep going to the left, it's going to keep going to the right. So from left to right, the domain is negative infinity to infinity. And the range is also negative infinity to infinity. Now, even though it looks like it's going to kind of flatten out, it's not really. It's just the nature of the graph. It's going to keep going to the right and up and to the left and down. It's just, unless we do a 100 by 100 graph, it's a little bit difficult to see that. But the range is negative infinity to infinity. The x-intercept is 0, 0. The y-intercept is also 0, 0. Now, the question is asked are y equals x cubed and y equals the cube root of x one-to-one functions? And the answer to that question is yes, because they are both functions. Okay, x cubed is a function and the cube root of x is a function. So since they are both functions, they can be considered one-to-one. Okay, looking at this slide is the same as we've done for every parent function that we've looked at, okay? So obviously B and H are underneath the radical, so therefore they affect the X values. Please remember B and H are opposite day. A and K are outside of the radical, so therefore they affect the Y's, and you do those at face value. Now, no matter what I do to this function, move it up, down, left, right, stretch, shrink, reflect. No matter what I do, the domain and the range will never change. They will always be negative infinity to infinity. And of course, the x-intercept is where the y is 0, and the y-intercept is where the x is 0. So again, this has not changed. All right, let's move on to example 1. So here we are looking at example 1. Y equals 1/2 times the cube root of x minus 3 minus 1. So let's describe that transformation. The minus 3 underneath the radical indicates that we're going to move to the right 3. The minus 1 outside of the radical indicates that we're going to be moving down 1. And the 1/2 outside indicates a vertical shrink of 1/2. Now, we always start with the parent function table, and then we have to ask ourselves, okay, how are we going to go from old x's to new x's? So it's x minus 3 underneath the radical. So remember, it's opposite day. So instead of subtracting 3, we're actually going to add 3 to each of our x's. Now, we have to ask the question, how do we go from old y's to new y's? And the way we're going to do that, remember PEMDAS says we multiply first. So we're going to multiply by 1/2 and then subtract 1. So when we do that, we get the following y values. So when we look at it on the graph, it looks like that. Now let's talk about domain and range. Now, again, we just said it doesn't matter if we go up, down, left, or right, stretch, shrink, reflect, the domain will always be negative infinity to infinity. And the range will also always be negative infinity to infinity. Now, the next question is asking, over what interval of the domain is the function increasing? Well, because we read our graphs left to right, this graph is consistently or constantly increasing. So it's increasing over the entire domain. So our answer to that would be negative infinity to positive infinity. It's increasing over the entire domain. Now, the only time this graph would show a decreasing interval is if that a was negative. If a was negative, then it would reflect that graph over the x-axis and it would go from increasing to decreasing. But if that happened, it would still be decreasing over the entire domain. But for now, the answer to the question over what interval of the domain is the function increasing is negative infinity to infinity. All right, let's talk about max and min over an interval. So I want to find the max and min over the interval for 67. So remember, that's left and right. We have to do f of L, f of h, f of r. This time my h value is 3. So I look and I say, is 3 in between 4 and 67? The answer to that question is no. It is not in between 4 and 67, so we don't have to figure him out. We just have to focus on 4 and 67. So I plugged 4 into the function, and I plugged 67 into the function. And 4 minus 3 is 1. 67 minus 3 is 64. Cube root of 1 is 1. Cube root of 64 is 4. And so if you look up above, the cube root of 1 is 1. Half of 1 is 0.5. 0.5 minus 1 is negative 0.5. Cube root of 64 is 4. Half of 4 is 2. 2 minus 1 is 1. So negative 0.5 is where is going to be the value for the minimum, and 1 is going to be the maximum. But please don't forget proper rotation. I apologize, not proper rotation, proper notation when you are writing the max and min. So we have to write f of 4 equals negative 0.5 is the minimum, and f of 67 equals 1 is the maximum. So don't forget that proper notation, because without proper notation, you will lose some credit for that. So now let's think about this logically. This function is consistently increasing. So since it's increasing the entire time, we really don't even have to think about h, because our max and mins are going to come from our endpoints since we are increasing the entire function. So really, for cubics and for cube roots, you do not need to worry about the h value. You can just simply do f of L and f of R. Now, let's find the x and y intercepts. So if you remember from every other lesson we've had, for the x-intercept, that is where y goes to 0. So we have to solve and we have to isolate the cube root. So to isolate the cube root, the first thing we're going to do is add 1. That gives me 1 equals 1/2 times the cube root of x minus 3. To get rid of the 1/2, we have to multiply by 2. And that gets me 2 equals the cube root of x minus 3. Then we're going to cube both sides because we have to get rid of the cube root. So we have to cube both sides. So when I do, I get 8 equals x minus 3, and then I add 3. So x equals 11. But remember, we can't leave it in this format. So we have to write it as a coordinate point. So that becomes 11, 0. Now, let's look at the y-intercept. The y-intercept is where x equals 0. So I plug in 0 for x, and I get 0 minus 3, which is negative 3. Now, there is no cube root of negative 3, and don't freak out. Remember, you can have a negative under the radical as long as the index is odd. So the index is odd, so I'm allowed to have a negative under the radical. Now, I can't really simplify this any further without getting into decimals and using my calculator, but remember, we're not going to have a calculator on our quiz. So leaving your intercept in this format is perfect. If that's as far as you can go, that's as far as you can go. You do still have to write it in a coordinate point notation though. So that's going to be 0, comma, 1/2 cube roots of negative 3 minus 1, because you can't take the cube root of negative 3, so you cannot go any further with that simplification. Let's look at example 2. Example 2 says, given g of x equals 2 times the cube root of x minus 2 plus 5, and f of x equals negative 2 times the cube root of x plus 3 plus 8. And I want you to describe the transformation from g of x to f of x. How did I go from g of x to f of x? Well, if you think about it, if you were to look at the center point for g of x is positive 2, positive 5. So if I'm at, and then the center point for f of x is negative 3, positive 8. So if I'm at positive 2 and I have to go all the way to negative 3, that's a movement of going left 5. Okay, now for the k coordinate part of it, the k of g of x is 5 and the k of f of x is 8. So that means I have gone up 3 because I was at 5, now I'm at 8. Now both the a values are 2, except g of x is a positive 2 and f of x is a negative 2. So since we went from positive to negative, that indicates a reflection over the x-axis. So that's how we describe the transformation. Because I'm like, okay, g of x I'm at 2, but for f of x I have to go all the way to negative 3. So 2 to negative 3 is left 5. I'm at 5, but I have to go to 8, so that's up 3. And then 2 to negative 2 is just the reflect across the x-axis. Now, this is an example that you can kind of pause the video here, and try to do this. And then once you complete all 7 tasks based on this function, go ahead and hit play again, and you can look at the answers and check your work. All right, so by now you've finished, and let's check our answers. There we go. That's what your graph should look like, and there's all the information for domain and range, max and min, x-intercept, y-intercept, all that good stuff. Okay, for example 4, you knew I was not going to let you get away without graphing a b-value. So we have to graph a b-value. So right here we have a b-value of 1/2, but the first thing we have to do is we have to factor out that b-value. So that's what I get. Because remember, if you were to distribute, you want to get back 1/2 x plus 4 if you were to redistribute. So my a is negative 2, my b is 1/2, my h is negative 8, and my k is positive 3. So since this has a b value, I'm going to use the double tables. So how am I going to go from old x's to new x's? Well, it says I have to multiply by 1/2, but remember it's opposite day. So multiplying by 1/2 would be like dividing by 1/2, which is really multiplying by 2. So I'm going to multiply by 2 and subtract 8. So this is what I get. Now to go from old y's to new y's, I'm going to multiply by -2 and add 3. And that is what I get. Now, obviously, -24/7 is really off the grid. I think I just threw them out there somewhere so we can have the curve. But you should be able to graph the rest of the points fairly easy. And that's what you get. And that's what it looks like. And here's the kitty cat to brighten your day. All right, let's move on to example 5. Now, this would be really gross if we tried to graph it, because who wants to divide all of your x values by 27 and either deal in decimals or fractions? Not me. So the process is still the same though, but we're still going to factor the b out. But this is the cube root. And do you notice that b is a perfect cube? If b is a perfect cube, let's pause for a minute and let's think back to when we had the square root. When we were doing the square root functions, if b was a perfect square, we could take the square root of b and bring it outside, right? Well, we can do the same with cube roots. If our b is a perfect cube, you can take the cube root of the b and bring it outside. So we can break this into the cube root of 27 and the cube root of x minus 3. So cube root of 27 is 3. So that becomes 4 times 3 times the cube root of x minus 3 plus 5. So 4 times 3 is 12. So that makes something that we can graph much easier, because this would just be, instead of having to divide each of the x's by 27, now I just have to multiply all my y's by 12. So if you have a b and it's a perfect cube, you can take the cube root and bring it outside to make your graphing easier. Now let's look at example 6. So this is finding the inverse of f of x. So remember, for f of x, to find the inverse, we have to switch x and y, and we have to resolve for y. Well, before I do any of that, I always change my f of x to y. Now that I've done that, I'm ready to start the first step. I'm going to switch x and y. Now I just have to resolve for y. So the first thing I have to do is I have to subtract that 4. And I get x minus 4 equals 2 times the cube root of y minus 3. Now, I'm going to go ahead and I'm going to divide by 2. So that gives me x minus 4 over 2 equals the cube root of y minus 3. Now I'm ready to cube both sides. Now, because I have a numerator and a denominator, I cube both the top and the bottom. So I end up with x minus 4 cubed over 8 equals y minus 3. I now add 3 to both sides. And remember, there's an imaginary 1 out there. So I'm going to, in the process of adding 3, I'm also going to pull that fraction, that 1/8, out front. So that way it is 1/8 times x minus 4 cubed plus 3 equals y. Now, of course, we probably want to switch this back into proper inverse function notation. So we have the inverse of f of x equals 1/8 times x minus 4 cubed plus 3. Okay, so hang in there. 4 more slides, and then we are done. So let's look at example 7. Example 7 says to determine if f of x and g of x are inverses. So we need to determine if f of x and g of x are inverses. So remember, the only acceptable test to prove that they are inverses is to do f of g of x and g of f of x. And if they both equal x, we're good to go. So I'm first going to do f of g of x. So that means I'm going to do f of the cube root of x minus 1. So what this means is anywhere I see an x in f of x, I'm going to substitute in the cube root of x minus 1, like so. Well, that minus 1 and that plus 1, they cancel each other out. So I'm left with the cube root of x cubed. Well, cubing the cube root undoes it, and we're just left with x. Now let's look at g of f of x. So that means anywhere I see an x in g of x, I'm going to substitute in x plus 1 cubed. So it becomes like this. The cube root of x plus 1 cubed minus 1. Now, that minus 1 is outside the radical. So I am taking the cube root of something being cubed. That undoes it and gets rid of it. And then I have x plus 1 minus 1. Well, now the 1's cancel out and I get x. Since they both equal x, I am allowed to say that f of x and g of x are inverses. Now they both have to equal x. Okay, if they don't, then you can't do it. You can't say they're inverses. But since these both equal x, we're good. They are inverses. Okay, now let's look at example 8. We've done this before. We did it with the square root and the quadratic function, so this shouldn't be anything terribly new. I want us to find the inverse of f of x equals x plus 4 cubed minus 1. So remember and then we have to graph both. So remember when we're finding the inverse, first of all, we make that y equals x plus 4 cubed minus 1. So the first step is we switch x and y. We switch x and y. Now we just have to resolve for y. So I'm going to add 1 to both sides. So that becomes x plus 1 equals y plus 4 quantity cubed. Now that the quantity cubed is by itself, I am allowed to take the cube root. So I get the cube root of x plus 1. And of course, that negates the cube. So we have the cube root of x plus 1 equals y plus 4. And then I just subtract 4. And then, of course, we write it in proper function notation. The inverse of f of x equals the cube root of x plus 1 minus 4. Now, this is the equation. We're not going to use this to graph, remember? So we're going to go back up and we're going to graph the original. Well, my original was x cubed. So my original function was the cubic function. So I'm going to graph that first. So to go from old x's to new x's, I'm going to subtract 4. Then to go from old y's to new y's, I'm going to subtract 1. Okay, so here is x plus 4 cubed minus 1. Now remember, the trick to graphing is all you have to do is switch the x's and the y's. And that's what I did. I just switched the x's and the y's. Okay, so now I'm ready to graph. So that's what it looks like. Now, of course, you don't have to put the diagonal y equals x line in there, but I just put that in there to remind you that the inverse is a reflection across y equals f of x. So the relationship between f of x and the inverse is that they are reflections over the line y equals x. Now let's talk about domain and range. The domain and range of the cubic function are negative infinity to infinity. Well, the domain and range, because remember we just flipped domain and range, but also the domain and range of the cube root is negative infinity to infinity. And then we've already talked about that, yes, they are one-to-one functions. All right. Last slide. I want you to perform the following function operations given the three functions f of x, g of x, and h of x. So I want you to pause the video right here and complete these 4 function operations, and then when you're ready to begin again, we'll pick back up. All right, let's check our answers. So for 3 times f of x minus 2 times g of x, this is what I got. Now, look carefully on the second line. You'll see that I changed that minus to plus a negative, and I distributed a -2. That keeps you from making sign mistakes. So if you have subtraction, change it to plus and negative, and then distribute the negative. It's going to make your math work so much easier. Now, part B is f times g of x. So f times g of x, that's a binomial times a trinomial. So what I did there is I boxed it, and you can tell my solutions there, and that's the answer I got. Now for part C, they want g times f of -2. So just like B was f times g of x. Part C, I want g times f of -2. Now, you could find g times f, which is the same as f times g, and you could plug in -2. Or you could do what I did, find g of -2, multiply it by f of -2, and get your 2 solutions, and then multiply your 2 solutions. So the first thing I did was g of -2. I plugged -2 into g of x and got -22. I then plugged -2 into f of x and got -11. Now I'm allowed to multiply my 2 results and come up with 242. Now, with part D, closed circles, if you remember, mean multiplication. Open circles mean compositions. So this means I'm going to do h of f of x. Now, me personally, I'm not a big fan of this notation for compositions, so I always change it to be h of f of x, where f of x is in parentheses. And then f of x is x cubed minus 3. So anywhere I see an x in h, I'm going to replace that x with x cubed minus 3. So I have -27 times x cubed minus 3 minus 81, the cube root of that, and then minus 5. So I distribute my -27. I come up with -27x cubed plus 81, but I also have minus 81, so that goes away. And I'm left with the cube root of -27 x cubed minus 5. And the cube root of -27x cubed is -3x. So -3x minus 5 is as far as I can go with that. All right, so again, going back over that example, in the top, I distributed the -27, and then I cleaned up under my radical, and then at last I was able to simplify that radical by taking the cube root, and then that expression of -3x minus 5 is as far as I can go. So that concludes our 5D.2 lesson. Your homework is worksheet 5D.2, which is available on Canvas if you weren't in class to pick it up. All right. Thank you so much. Y'all have a great day.